Wie war das? So we have about 50 minutes left. We will start right on time. For those who are already logged in. So please be patient, about 15 minutes left. Webcam angeschlossen. Komm, plug it in. Machen wir mal für dich aus. Test. Ich muss dich jetzt erstmal dazu fügen. Peter, kannst du mich hören? Peter? Soundcheck 1, 2, 3. Ich höre dich super, alles gut. Okay. So. Kannst du die Präsentation schon mal aufmachen? Kannst auch schon was von stumm schalten. Sonst hören uns alle, die eingeloggt sind, hier stumm. So we have 3 minutes left. We will start right on time. So okay, everybody, it's 2 p.m. Welcome to our second webinar. This time, my colleague is going to talk. My colleague Konrad Seidel is going to talk about FeFET memory devices. We are broadcasting live here from Dresden in Germany. Thanks for joining us. The presentation is going to take about 1 hour. You can ask your questions by typing them in, and we will clarify these questions after the presentation. So unfortunately, the slides are not available yet. I will send them to you, I guess, next Monday, because we have to make a different version of it, so you will get it. Yeah, I think we are ready. I think we can wait. I don't know. Let's start on time as promised. Konrad, are you ready?
Yes, I'm ready. Peter, okay. Thank you for your introduction. Also from my side, hello to everybody, and welcome to our webinar about FeFET memory technology. Yes, for introduction, yeah, I'd like to show a world full of memories. I like to show that the world is full of memories. Yeah, you know, in many applications we have different kind of memories. Even in the dustbin, there is a hidden storage for ID tracking. And yeah, so for each of those applications you see on the right side, there are, of course, different memory solutions on the other side you can embed in such applications. And of course, it's always difficult to find the right memory solution for those applications. Yeah, there are a lot of criteria to be discussed when selecting such memories. So among a lot of other solutions, among a lot of other requirements, there is the speed, latency, the storage size, it's the power consumption, data retention, form factor, also the number of read and access cycles, bit error rate, and so on. And yes, looking at speed, latency, and storage size, there's this famous memory hierarchy, which is focusing on such criterions. On the one side, you have the capacity, meaning that you have in more in a larger storage capacity on on a larger form factor. And on the other hand side, if it comes closer to the core devices, you have higher speeds, but high capacity and also high speed is always a challenge. And you can see also among at this memory hierarchy that only in this classical approach, only the non-volatile memory storage is the storage is only non-volatile for the larger form factors and also larger capacities. And if it comes to faster operation, it will be then in that case not a volatile memory solution. Yeah, but this doesn't tell us about power. What is power? Yeah, also form factor, and also how to find the right memory solutions in order to build small size, low power sensor nodes. Yeah, that means we have to think differently about this memory hierarchy, and we have to bring more and more non-volatile functions also to the core devices. And this is one task among others for the so-called emergent memories in order to close the speed gap between the core device, the fast operation, and the larger storage densities. And there are several memory solutions discussed. And among such solutions, also the FeFET memory technology is one of the potential candidates for for bringing non-volatile memory capability closer to the core devices. The FeFET itself, or generally the ferroelectric memories, have already a long history, and maybe it's worth to mention that first patents were already about FeFET were already placed in the 1950s, but yeah, there was not such a strong breakthrough until the until 2007 and years after, because there the ferroelectricity was discovered in silicon-doped hafnium oxide material. So it was the first time that you have a CMOS compatible material which shows ferroelectric properties. And then this brings just a kind of new development also for future applications, also in the direction of scaling. Of course, there are also alternative or other memory concepts based on PZT materials, which are also widely used, but they are not suitable for front-end implementation. Yeah, so hafnium oxide, what is the material? We will discuss on the next slides. But first of all, I'd like also to say that the drivers for such ferroelectric for this new ferroelectric drive are the CMOS compatibility, the scalability, low power capabilities, and also the possibility to address various new applications. If you look at the publications at the IEEE publications addressing ferroelectricity and hafnium oxide, then you see that it's tremendously increased in the past years. And if you compare it with the generally ferroelectricity and memory, it's superimposed by this hafnium oxide based ferroelectricity concepts. And if you look at the quite a new field, ferroelectricity together with neuromorphic computing, yeah, we will expect for the future also some more movements. I will talk about this also later in my slides. In the Dresden region, the ferroelectric hafnium oxide has, yes, from the beginning a long history, and there is in Silicon Saxony, ferroelectric memories are developed since more than 10 years, and strong partners are here, Global Foundries, Ferroelectric Memory Company, and also NAMLab, and we are here in a close collaboration in this region. Yes, now my webinar will address the classification of ferroelectricity, then also how we get the hafnium oxide ferroelectric, which is a major criterion for memory operation. Then also we will discuss how to integrate hafnium oxide into a memory cell, also discussing different concepts. Then I will just give an introduction about the FeFET research platform at Fraunhofer IPMS and the possibilities for further research and development on that field, as well as some examples with results of reliability and characterization. And also finally, we will discuss future trends of ferroelectric field effect transistors. So ferroelectric in general. The ferroelectrics are materials with spontaneous polarization, and they are part of dielectric materials, as you can see in this classification. I will come later to that point. Ferroelectric hafnium oxide also shows, of course, that in that case, pyroelectric effect. It's also piezoelectric and, of course, dielectric, since it's just a subclass of such dielectric materials. If you look into the ferroelectric behavior, how it comes, it requires a crystal structure with polar axis in order to have two stable states. This is shown here on the example of barium titanate, where you can see that you have with such iron two possible states inside the crystal structure. And what happens actually in order to switch this is you need to exceed a certain coercive field in order to change the polarization and switch the state. So talking about hafnium oxide, hafnium oxide comes in a can be realized in different phases. For instance, monoclinic, tetragonal, and cubic. It depends on the temperature, the stress, the doping, and also confinement, the general process handling of the material and the films. But for electricity, as I said before, we need non-centrosymmetry of this film, and this requires the so-called orthorhombic phase, which is the only phase which can be switched and polarized. And for getting to that phase, that special phase of hafnium oxide, you need a certain special treatment of especially certain stress conditions, and also doping is possible. There are different dopants discussed for achieving ferroelectric behavior. Yeah, and now back to this picture. So as I said, every ferroelectric material is also showing pyroelectric properties, also piezoelectric properties, and is of course just a part also of the dielectrics. This means there are, based off those properties, there are different applications possible. For instance, temperature sensing due to the pyroelectric effect, also implementing robotic devices due to the electrorestrictive behavior, also of course linear capacitors due to the dielectric behaviors, for energy harvesting because of the piezoelectricity. Also electro-optic properties are possible to use for different applications, and finally the ferroelectric property for the memory applications. In our webinar, we will of course focus on this field. Fraunhofer IPMS also does research on those other topics, but this is not focus of today's webinar. Yeah, so for the ferroelectric memories, there are different options for implementing them. One is the so-called FeFET, which means you have the entire ferroelectric material directly embedded in the gate stack of the transistor, which has the advantage that you have one transistor cell size, you have non-destructive readout, you have the advantage of course, front-end integration, but also a disadvantage because you have to deal with a lot of CMOS compatibility and also achieve a kind of dual integration, not to distort the general CMOS capability. And you have to handle, due to the interfaces, due to the lower K interfaces, you have to handle the depolarization effects. On the other hand side, more commonly known is the FRAM solution, which means that you attach just to the zone side of a transistor this ferroelectric stack. This can be realized in the backend of line and is realized in backend of line also with PZT materials in standard applications. So you are more independent from CMOS. You have the advantage due to the symmetric stack, two metals on both sides, each of the sides a metal layer. You can have also better endurance and reliability behavior, but it's difficult to scale the capacitor. And for reading out, you have to switch the material, and this means you have a destructive readout memory concept. And also for implementing the materials, you have to mind, especially in backend of line, you have to mind zonal budget requirements, which is also limiting the choice of ferroelectric materials, which you can use. Of course, you need to crystallize them also at lower temperatures. First of all, we will discuss the FRAM concept. For the FRAM, yes, it is required, like in DRAM, that you need to switch. In order to detect a state, you need to switch a considerable charge. And so the storage depends on the charge per area. That means it's required to have, to read out an FRAM cell, to have a larger capacitor area on a small form factor. And for that, Fraunhofer IPMS investigated different solutions in the direction of 3D scaling, which is shown here. That means the ferroelectric material is implemented in a 3D in deep holes, and yeah, it was shown that we could boost the capacitance and the polarization by implementing the ferroelectric layer into deep holes, which is shown here. In addition, it could be shown that the ferroelectric material showed a saturated endurance of 10 to the 9 cycles. This is due to the symmetric stack. On the next page, just the scaling shown with the different array sizes for deep holes, and also for larger arrays, it's can be seen that it shows the saturation that's just based from a test chip, that you can achieve a strong gain in polarization behavior. This is because of the parasitic share, which is more prominent for the smaller sizes of FRAM array. What you can see on the right side is the required and very good, well-achieved conformality of the film deposition down to the hole of this bottom side of this trench, which proves that we have a stable ferroelectricity into the deep hole. Now let's talk about the FeFET. So first of all, I'd like to introduce the FeFET itself. So the FeFET consists of, yes, it's from the construction point of view, it's similar to a MOSFET. The only difference is that you place in the gate stack a ferroelectric layer, which is shown here. And in normal case, you have also a small interfacial layer with, in most cases, low-K dielectrics, and a capping of tinitride on top. If you read it out, in the initial case, you get also a kind of normal IDVT characteristic. And now, if you switch the material, if you apply positive voltage on the gate in order to program the material, in this example, it's 6 volt, then you shift the VT of the device. And that means you have to exceed the coercive field in order to switch the material, and then you can detect by reading out at a certain current criteria or voltage criteria, you can read out the shifted VT. If you apply a negative voltage onto the gate, then you switch the VT to a positive level. and the difference between positive and between low and high VT is called memory window, which is shown here. As you can see, there is a difference to a floating gate flash. So normal case, floating gate, if you program, you increase the VT. For the FeFET, the polarization works against the field. That means if you program the device, apply positive voltage, you shift the VT in the negative direction. And if you raise the device, you shift the VT into the positive direction. This is very important, and this helps also to differentiate this ferroelectric shift to trapping mechanisms. On the other hand side, it's very dangerous because, or it's crucial to avoid in ferroelectric memory devices trapping behavior, because if you superimpose trapping with ferroelectric switching, this would reduce memory window and also endanger reliability. The target, of course, for the optimization is to achieve a large memory window. And the memory window is, there's a universal relationship between memory window and also the coercive field and thickness, which is shown here. And for instance, the PZT and also SPT materials, they have a lower coercive field and require a much higher thickness, which is hard to implement in CMOS scale devices. So it's shown here, you need a very thick stack in order to switch the material in this with this planned memory window of in the region of 1 to 10 volt, as shown here. The hafnium oxide, ferroelectric hafnium oxide, has a much lower K value, but it's of course part of the high K value, but it's in the range of 20 to 30. And this low K value also induces a higher coercive field, much higher coercive field, which allows us to reduce significantly the thickness, as shown here, of the gate stack, so that we can operate the device in the range of 10 nanometers thickness. Yes, this also shows the advantages of hafnium oxide-based FeFETs, and also the strong momentum which was achieved by the discovery more than 10 years ago. So you can achieve low power switching. You have, by implementing it into this FeFET architecture, non-destructive readout. Due to the already widely used high K material hafnium oxide, it's CMOS compatible. This material also shows fast switching and also scalability. This was already shown, for instance, in IDM by publication of Global Foundries, that it was already implemented in memory arrays, and also yes, shows a considerable memory window and functionality. This was first time demonstrated the ferroelectric memory in an array. At Fraunhofer IPMS, we implemented a test platform for material development and further development on ferroelectric memories, which is consisting of more simple devices and a kind of short loop concept, which is featuring a standard FeFET device, different standard FeFET devices, and also a matrix of different dimensions. The advantage of this platform is that it's also processed on 12-inch substrates, and so we can investigate wafer uniformity and also different process strips, splits, and it consists of a large number of dies all over the wafer in order to increase the statistic, and we have also variation of the dimension, also checking local variability and addressing different structures for process monitoring. One of these examples is what we can do with this platform is split analysis for instance, in order to optimize ferroelectric material, which is shown here. So different wafers are processed with different dopant concentrations of hafnium oxide, and then you can easily identify the sweet spot with the maximum memory window. And as already mentioned, we can investigate wafer uniformity and also cross-flow issues, whatever. So we can also check the reliability and variability of those memory concepts. This is platform is optimum for unit process development. Our institute is located in Dresden. We are Fraunhofer IPMS with different subsidies also in Thüringen and Brandenburg. And in Dresden, there is our headquarters, but our location is the Fraunhofer IPMS Location Center for Nanoelectronic Technologies, which is located, which is embedded in the Infineon campus of Dresden. And we share the clean room with Infineon. And we have there, a part of this clean room is 12-inch research facility with industrial grade tools. CMOS compatibility is maintained, and we do ferroelectric research since 2008. Back to the processing flow for our FeFET short loop research platform. There are several options to collaborate with partners. So one option is, of course, the entire wafers are processed at the wafers are processed entirely at Fraunhofer IPMS, and we deliver test data to our customers and research data to our customers. But it's also possible to that we pre-process wafers and the customer can investigate high-K or ferroelectric materials, and then the wafers are finalized at our site. But it's also the other way around, that we can, of course, do reference processing of ferroelectric materials on customers' material and also on customers' test chips, supporting also electrical characterization. Of course, this kind of short loop, this loop lot concept is based on CMOS standard, so it's possible to exchange wafers with facilities worldwide, also production facilities. In addition, in order to support the characterization, there are different physical characterization techniques established at Fraunhofer IPMS, like a TEM, SEM analysis, also PFM analysis, TOF-SIMS, XRD analysis, and here are some examples shown from such an analysis variety which is required in order to understand the materials. For ferroelectricity, I'd like to highlight one analysis method which is for understanding, deeper understanding of grains with ferroelectric behavior and differentiating the grains and the grain orientation. This is the so-called TKD analysis, the transmission Kikuchi diffraction technique, which is based on electron backscatter diffraction, EBSD, which such patterns are collected in the scanned regions. This TKD analysis allows the understanding of grain size distribution, then also understanding of the local crystallization phase, also understanding about the crystal phase fraction, so, and also the crystallographic orientation of the materials. For electrical characterization, we have a well-equipped lab for supporting memory characterization on single chips up, but also 200 and 300 millimeter up to full lots of wafers, covering a test temperature range from -60 to +300 degrees centigrade. And it is possible to do NVM single cell parameter test to understand over a large statistic NVM parameter, but it's also possible to do detailed NVM characterization. And we have a full testing environment covering with a coverage from bit cell over test array to the final solution, which is maybe an embedded or standalone memory array with higher storage density. For that, mixed signal test system with multiple channels and multiple analog sources are used. So how far did we get with this webinar? So we discussed the classification of ferroelectricity, also how to get the hafnium oxide ferroelectric, how and the different options to integrate hafnium oxide in a memory cell. I showed the FeFET research platform at Fraunhofer IPMS, and now I'd like, based on this research platform, I'd like to show some key results, some characterization and reliability data from this platform, showing also the direction of research and the topics which are discussed for the FeFET. So one important thing which we have to keep in mind, we saw it earlier with the cross-flow pattern or with the wafer non-uniformity, is based on this formula that a small variation in thickness causes a strong change in memory window. That means it is very crucial to have a good process uniformity over the wafer in order to achieve stable ferroelectric behavior over the wafer and a stable memory window for the memory arrays. Another important thing is, of course, the doping as the material, as I mentioned earlier. I'd like to give two examples. Of course, there are also more dopants possible, but we focus on silicon and zirconium doping. So for the hafnium silicon oxide, which is shown on the left side of this diagram, you see that you can, by changing the silicon doping concentration, you can change the memory window and also boost the ferroelectric behavior and optimize it. And also, if you you can also, it's also demonstrated that if you do not achieve the ferroelectric behavior in the film, you also get trapping behavior with negative memory windows. For doping with zirconium, you can also achieve even higher memory windows, higher polarization coefficients. This is also another potential material which can be used in different applications, but we will discuss this later, not for the front-end applications. Back to the variability, as mentioned above, a little change in thickness or also dopant concentration, as shown here, can have an impact on memory window, which is shown here. So especially hafnium silicon oxide is very sensitive to this effect of thickness and concentration variation, which leads also to a larger variability on the program side, on the erase side, and then also in the effective memory window. So that means one focus of the material optimization is to get this non-uniformity, to reduce and mitigate this non-uniformity over the wafer. The hafnium zirconium oxide is less sensitive to dopant concentration and also thickness variation, and this is also shown here that here in this case, compared to hafnium silicon oxide, it has a lower variability. But also, what you can see here, it is possible to achieve in both cases memory window. But selecting the right material is also a topic for integration. You cannot easily integrate every ferroelectric material. You have also to mind the thermal budget requirements for this, and in that case, especially hafnium silicon oxide is the candidate for front-end integration. Now I'd like to give some examples for reliability topics and tuning the FeFET for reliability. Some reliability detractors for the FeFET are trapping, as I already discussed earlier, interface breakdown, but also the depolarization behavior. That means the interfacial layer, which you can see here, which is a little bit yellow, is in most cases a low K film, or has a lower K compared to the high K, and it's causing a field which is working against the polarization field, and this causes then in that case the depolarization of the ferroelectric capacitor, and in that case retention issues. Yeah, generally we have an asymmetric stack for the FeFET, and this has a strong impact, of course, on the retention, on the endurance, and also on the wake-up behavior. Most of it can be addressed by interface and stack engineering, which we do in our research in order to mitigate such effects. So what is the goal for the interface layer optimization? So for instance, the modified stack field distribution for we need a modified stack field for low power operation. So of course we have to keep the voltage as low as possible for the switching. Then in that we have to for that we have to reduce the field at the interface layer, which is shown here, and we have also to reduce the depolarization field in order to enhance the retention. So when you look at the dielectric behavior of this interface layer, which is can be considered like a dielectric, you have different knobs. You can reduce the thickness of the interface layer. You can increase, of course, the area, but this is of course not possible due to this embedded gate stack. And you can increase the permittivity of the interface layer. Such options are discussed, and in order to get the capacitance of the interface layer, increase the capacitance of the interface layer, and reduce the voltage drop on the interface layer, you have to increase the permittivity. And for this, we propose silicon oxynitride as interface layer compared to silicon oxide. Some examples, characterization examples are shown below. So as you can see, the silicon oxynitride interface layer allows a switching as much ferroelectric switching at much lower voltages compared to silicon oxide interface layer of same thickness. On the other hand side, it improves as well, as we can see based on this discussion earlier here with the voltage drops and the stress over the interface layer. It also improves the retention behavior, as you can see in this diagram, and also it improves the endurance behavior and also improves the retention behavior, which you can see on the right side. To summarize it, so higher permittivity of the interface layer is very beneficial for the FeFET operation. And of course, this is also very dependent from preventing silicon oxide interface layer growth. Yes, furthermore, I'd like to give you some examples about the switching behavior of FeFET. So if you apply very strong high voltages, then you get, of course, a fast switching. You can impact with the voltage, you can accelerate the switching behavior and get also very high memory windows. Also, applying different voltages, you can see that at least for larger devices, you achieve a multi-level switching due to the ferroelectric grain variability. And at elevated voltage, you have also what you can see here, trapping mechanisms coming into the game at longer pulse widths, which then reduce the memory windows. So this is also something, a topic for optimizing operation schemes of FeFET in order to get good reliability, in order to achieve good reliability and high memory windows. And with longer pulse widths, you won't get more improvement of memory window, so it more or less saturates then, and we have no further memory window increase. We stay at the scalability. So for, as I mentioned, for larger devices, this is valid that we get a kind of gradual switching behavior. But if you decrease the devices, then you will also find some devices with an instant switching effect. So if you reach the coercive voltage, it suddenly switches, and then you get to the program state in this example. So scaling the device increases the variability, which can be seen also here. If you measure a larger indiced statistic of the same devices, you have for larger devices, you have a lower variability compared to smaller FeFET devices. For the scalability and the switching behavior, yeah, this could be addressed, of course, different applications. As already discussed, so with the single domain switching, you have only one state in between. If you, but also multi-level storage is possible if you have multiple cranes with a certain variability. In that case, you can also achieve one or multiple states in between. Achieving multiple states is one topic for neuromorphic applications, which I will discuss on the next slides. But first of all, this picture indicates just the crane variability, why we have analog states in between and not just two states of switching. This is because cranes could have different orientation, and also not the full FeFET might be in the not the full film might be in the orthorhombic phase, so that you have also inactive cranes inside. So that means it's an intrinsic behavior of FeFET that you can also achieve analog switching behavior, and this is very good for neuromorphic applications, which I show on the next slides. So the threshold voltage of the device can be changed by switching domains, and if we look onto the pulse behavior, the pulse number, it can be also shown that we can switch the material in a nearly linear region, and also that means this is mandatory behavior for neuromorphic applications, that you do the potentiation and depression in a linear scheme. On the left side, you can see that the linearity factor can also be enhanced by selecting the right readout gate voltage, which is in this region. If you increase this region at 0.8 volt for this example, we get a quite low non-linearity coefficient, which then also transforms into a very good linear switching characteristic for spiking neural network, for instance. Yeah, so possible applications of this behavior is multiple storage, as already mentioned, machine learning, acceleration, and also neuromorphic computing. Due to the low voltage, low power operation, it is in the world of neuromorphic computing also possible to get rid of such kind of embedded memory array block inside inside a device. You can also distribute the memory in or within the logic, and this enables then also more advanced computing architectures, and you don't need to establish any more classical array architecture because of the lower voltage operation. Now I'd like to come to my last slide, discussing about future trends, what we learned out of this webinar. So for the technology, there are different options for further optimizing the interface for the FeFET in order to enhance reliability and variability. Then for the scalability, also for addressing as well the variability, there are also alternative ferroelectric layer concepts possible. And one is proposed by my colleague at IADM December this year. Then also the integration as kind of MFMIS concept. So that means you separate the ferroelectric layer from the gate stack, but place it within the gate, above the gate. In that case, you are more independent from the CMOS integration. This could be a potential concept as well for the future. And addressed applications are embedded memories, of course, but also neuromorphic computing, where we see also a strong focus and a strong advantage of ferroelectric memory devices. So to summarize my webinar, we discussed first of all memories and applications, also the importance of memory, emerging memory memory concepts in order to get non-volatility into the computing architectures. Then we discussed hydrogen oxide for the ferroelectric memories, how it is used, how is it integrated. Then I proposed the FeFET development platform, also enabling or allowing loop lot concepts together with partners. And finally, I presented research activities around our FeFET concept in the direction of neuromorphic computing, switching behavior, material optimization, and so on. I'd like to thank very much my colleagues and the entire CNT team contributing to this talk, and of course our partners, our funding partners and industry partners supporting our activities at Fraunhofer IPMS CNT. And I'd like to thank you for your attention. Finally, I'd like to announce the next webinars, which are about automotive LiDAR technologies on October 24th. Then Fraunhofer IPMS micro mirror arrays, versatile spatial light modulations on November 19th. And the power of micropump, a big idea in a small package on December 5th. Thank you very much.
All right, Konrad, thank you very much for your thorough introduction to FeFET memory. As far as I can see, there are two questions on slide 29. You introduced the terms or the abbreviations SPT and PZT. What does that mean, is the question.
Yeah, so SPT is, sorry, this isn't written as a long name. SPT means strontium barium titanate, and PZT means lead zirconium titanate. And these are specific materials which are used for, which show ferroelectricity, and which are used also for FRAM memory concepts.
Okay, thank you. And the other question is on slide 64. No, 46. Sorry, 46. You showed the programming voltages between 4 and 6 volt. Yes.
Yes.
And for which technology were these curves? And could you program with a lower voltage around 2 volt if your pulse is longer?
Okay, that is first of all the question. Can you repeat the question of the programming voltage from 4 to 6 volt?
Yeah, you showed the for which technology were these curves? That is the question, the first part.
Okay. So okay, for which technology? So this is just of course it's done on our independent FeFET research platform. So it's not addressed to a certain specific technology node. Of course, there is a strong wish and demand for low power, even lower power operation, and this requires further stack scaling of the ferroelectric memory cell. This is correct. For this graph is more or less indicating the dependence on the film on the switching behavior from pulse width and also switching voltage. And for the technology addressed here, this is would be then that case, of course, a kind of technology which can supply in the range of 4 to 5 volts for programming racing voltages. Of course, it's possible to even more reduce the switching voltage. Maybe we can go to this diagram shown here with the potentiation and depression. Of course, the voltage is shown, but you can see that at least the number, the pulse length, or the number of pulses also impact in a certain range linearly the memory characteristic, the memory window. But there is, of course, an intrinsic switching behavior of the ferroelectric memory of the ferroelectric material, the so-called coercive field. And for that, you have to scale down the thickness of the stack and optimize it further. This is, yes, the challenge of our current work and also of future work, and yeah, would be going on.
Okay, thanks. Two more questions popped up. One is, I'm not sure which slide he's referring to, but the question is, how stable are your intermediate states?
Yeah, so the retention behavior of these intermediate states are, according to our investigations, very stable. Since this is not related to any trapping or other mechanisms, you really switch ferroelectric domains, and therefore this is based on retention tests also quite stable.
Okay, thanks. And the last rather general question, what is the main advantage of a FeFET memory compared to other emerging memories such as RRAM, PCM, and STT-MRAM, etc., especially for neuromorphic computing applications?
Yeah, okay, this is a very interesting question. Of course, every memory concept has its pros and cons. So when, making the question more precise into the direction of neuromorphic computing, what I can say is that we achieve excellent linear switching behavior of the FeFET memory concept. And compared to other concepts where it's a bit of more challenge to switch in such a linear scheme. And the other advantages are, of course, the fast switching behavior, and also the switching energy required is also quite low, because theoretically it's quite low, because you this is the only electrostatic memory concept. In the other memory concept like resistive RAM and also MRAM, you have to drive a current through the cell in order to switch, and here also you have to bring in more energy. But of course, for the FeFET, even if it is charge-based, you have to, of course, charge and discharge some kind of infrastructures in the memory array, which is also, of course, then contributing to power consumption. So this means for the FeFET, in terms of power, the power advantages, you can only gain the power advantages if you also make a careful design on the FeFET memory array. Of course.
All right, thank you very much. Sorry.
Of course, if there are further questions, you can also come directly in contact by email with me, and we can do follow-up discussion.
Yes, that was I was about to say that, because a few more questions popped up. I suggest you please contact Konrad Seidel directly if you need further information below, because there are too many questions left. Sorry about that, because we are running out of time. Thanks again for joining us. Thanks again, Konrad, for your presentation and for your time, for joining in. I will send you the slides on Monday, or yeah, I guess on Monday. And I hope to see you soon again for our next webinars. The next one is on October 24th on LiDAR technologies. And as you can see in the slides, there are a few more coming up. Yes, thanks everybody. Have a nice day, and best regards from Dresden. And I hope to see you soon. Thanks again. Goodbye.
Thanks also from my side. Thanks, Peter, for organizing.